Yeah, so hello everyone. So the topic of today is meshing using Hypermesh. So in this webinar, basically I'd be telling you about what is Hypermesh, why is it being used in the industry, what is the advantage of this software over the other pre-processing software which is currently there in the industry. Then after that, I'll be telling you about some of the disadvantages, then giving you a basic preview about meshing, and then I would be delving deep into the details of meshing part and be telling you as to what are the quality parameters you need to ensure while carrying out meshing. Okay, so this is the basic preview of the seminar. So let's start. So what is Hypermesh? So basically, Hypermesh is a CAE software. Now, what is CAE? CAE is computer aided engineering. Okay, so CAE is a big umbrella in which FEA is one part. Under FEA, Hypermesh is one of the pre-processing softwares. Okay, so Hypermesh is basically a product of a company called Altair. Okay, so uh, when does the role of Hypermesh comes? So suppose you're working in a design office and you are an FEA engineer or a CA engineer. Okay, so the role of Hypermesh would be coming after the model has been developed by the design engineer or product engineer, and they want to check as to how that model would be behaving in real-time condition. Okay, that model can be a car, can be an aeroplane, can be an oil and gas equipment, can be a medical device equipment, any of the equipments. Okay, so in that case, you might be carrying out some pre-processing operation. So that is where Hypermesh comes into play. So basically, Hypermesh is a pre-processing software. Okay, so in which we divide the model into set of elements and nodes, and then we apply the respective boundary conditions or respective partial differential equation to solve and get the interpret the results and see if it is as per our expectations or not. Okay, so basically pre-processing is used to mesh a model. So so apart from that, Hypermesh as a software is a very powerful software. It has an ability to generate high quality mesh with various capabilities like automatic, semi-automatic, shell meshing capabilities, and you can easily generate tetra, hexa mesh also. Then, like, it is, since it's a very powerful software, it gives more control to the user. Okay, and also helps in simplifying the modeling process of complex geometry. So basically, especially if you take industries like automobile or aerospace, so they are having very complex systems, very complex machineries, or turbo machinery industry also. So in such industries, the components which you might be working on are very complex. Okay, so if you want to mesh it, you need to be having a software which is very powerful and it can take the amount of take that much of complex geometry and is giving you a very good high quality mesh. So that is where Hypermesh comes into play. Okay, so by using Hypermesh, first of all, you can easily mesh complex assemblies. Then you can automate the meshing process. You can in aerospace industries, you might be working with laminate composites. Even that you can model with you can model seamlessly using Hypermesh. Okay. Now, what are the benefits of Hypermesh? Why is this software being used extensively in the industry? So it's, first of all, it's basically a very powerful modeling solution for the company, for any organization. Then it ensures high quality meshing with a very high speed, because since I told you, it gives more control to the user, and it has too many options, too many features, which helps the user to carry out meshing operation with ease and seamlessly, hence saving a lot of time. Okay, so apart from that, you can also automate the mesh model, and you can use batch meshing feature or functionality to improve your meshing speed. Means, for example, suppose you are making a product. Okay, so you can't release a product in the market with just carrying out one iteration. Okay, one day a design engineer thought that, okay, we want to make a product, we made the product and we just released in the market. That never happens. A product, before it releases in the market, has to undergo numerous iterations. Okay, in that, in every iteration there might be some changes to the product, and that every change needs to be checked in FEA. Okay, so that means you might have to modify the mesh again and again, or remesh again and again. So instead of doing that, if the changes are not that big, what you can do is you can simply automate the full, you can mesh it first time, you can simply automate the model, and where all changes are required, you can do that. So in that sense also, Hypermesh is very powerful tool. So basically Hypermesh has a functionality called TCL TK scripting. So that can be used to automate the meshing process. Okay. Then, then apart from that, it has capabilities of batch meshing, mesh morphing, connector modeling. So yeah, it is an integral part of PLM. What is PLM? Product lifecycle management. So as I told you, like any product would be undergoing numerous amount of iteration before it is released into the market as a final product, right? So in that case, you need to be having a powerful software in which you can modify the components with ease and you can remesh it like easily and again and again. Okay, so in that case also Hypermesh plays a very important role. And it uh, with that, since the software is giving control to the user, you can control the quality and the flow of mesh throughout the component or throughout the load transfer path. Okay, apart from all these advantages, the main advantage why companies are using is it supports a wide range of solvers. Okay, like Abacus, Ansys, Nastran. So basically what does that mean? Okay, suppose you're working suppose an aerospace industry is mostly using Nastran, or they are using Abacus, and an automobile company is using Ansys. But okay, they are okay with using the solver of Ansys, they trust the solver of Ansys, but they want a powerful pre-processing software. So that thing Hypermesh gives. Okay, so what does that mean is like you before starting the meshing operation, you can set as to for which platform you are using this meshing for. So if you just select on Abacus, you can mesh it considering all the functionalities in Abacus, and you can prepare a deck file which you can directly submit for run in Abacus. Okay, and you can get the results. Similarly for Ansys, Nastran, Mark. So that is the reason companies are preferring Hypermesh as a pre-processing software. Means companies in which their modeling, their geometry is way too complex, and they want high quality mesh because quality is directly proportional to the correctness of results. Okay. Yeah. So coming on to the pre-processing part. So what is pre-processing? So finite element analysis basically involves three major steps: pre-processing, solving, and post-processing. Okay. So pre-processing is the one in which you would be modeling the actual component or the actual product using FEM by disintegrating into a set of elements and nodes. Okay. So pre-processing involves following steps. Okay. So I'll just give you an example to explain it properly. Suppose the design engineer or you are working in an automobile company, they gave you a car model to carry out some crash testing. Just take an example of a crash testing. Okay. So they said, okay, we want to carry out a crash testing. The speed of the car hitting the wall should be suppose 60 kilometers per hour. Okay. So that is the requirement. After that, you as an engineer or as an CFE analyst needs to understand which all components is the area of interest for the requester or for the product engineer. Based on that, you can defeature the components which are not very much relevant for the analysis. Okay, some very small holes, bolts, spot welds, or nerves, curves, lines which are not relevant for the analysis. You can defeature them or remove them from the analysis, and in order to simplify the model. So that comes under model cleanup and designing. Okay, so after you have simplified the model for your analysis, you have discussed with the product engineer regarding the requirements, then you can start the meshing operation. Okay, so while meshing operation, you need to first of all select the type of element. Okay, or assign the geometrical properties. Means whether you should be carrying out 2D meshing, 3D meshing, or what kind of elements you want to use. Is it 1D, 2D, 3D, or uh, beam element, or shell element, or hexaedral element? So all these things would be coming in the next step. After that, you'd be applying the material. So depending upon the kind of analysis you're carrying out. Suppose you're carrying out a, yeah, so as I told you, you're carrying out an explicit analysis. In that case, if you want to capture the cracks or anything like that, you might have to go with a complex material model. Or else if you want to just, if it's a simple analysis, you can go with a linear elastic analysis. So based on that, you would be assigning material properties. Okay. Then after that, you would be applying constraints and boundary conditions to the model. So basically in that, you are actually making the car move at the speed of 60 kilometers per hour, right? So you will apply that initial velocity to that car. Okay. Then application of loads also comes into that. Now selection of analysis type. So basically you want to carry out crash testing of the car, right? So for that, the most relevant analysis is explicit analysis. Okay. Softwares which can be Radios, LS Dyna, or Abacus Explicit. So you can use that, right, as a solver. Okay. So this all these things comes under pre-processing. Okay. Now, why do we need to carry out meshing? So first of all, any domain, any component which you are using or going to carry out analysis for would be having infinite degrees of freedom, because if someone asks you how many points are there in that component, it is infinite, right? You can't actually say a number for that. So in that case, if you are actually solving for an infinite degrees of freedom, you might never be able to solve the analysis. Okay. So yeah. So yeah, you would never be able to solve the analysis. So that is why what you do is you disintegrate the analysis. Okay, you disintegrate the components into a set of elements and nodes. So in that case, what you're doing is you are reducing the degree of freedom from an infinite value to a finite value. So yes, just take this example of this circle. So here the number of points are infinite, but since you discretize the mesh, the number of nodes reduced to 8. Okay, so the number of equations also reduced to a finite value. So that means you are able to solve this analysis in a required amount of time. So that is the main reason for carrying out meshing. Okay. Yeah. Now, so I have given you a basic preview about the uh, type of meshing, uh, like what is meshing. So I've given you that. So now let's move on to the types of elements which are being used in the analysis. Okay. So types of elements can vary from 1D, 2D, 3D, and others. Okay. So hello, Balaji.
Yes, yes, Akhil.
Yeah, someone is again and again requesting remote control of the screen. Can you please?
Okay, one second, I'll just check that. Yes, Akhil, you are able to hear me?
Yeah, yeah, yeah.
Okay, you are getting some updates.
No, someone is requesting a remote control of my screen. I don't know why. I mean, it's blocking the screen, I believe.
Okay, okay, one second, Akhil, I'll just check that.
Yeah.
Yeah, Akhil, is it okay now? Is it possible for you to proceed?
Yeah, now I can continue. Yeah.
Yeah, yeah, okay.
Yeah. So there are different types of elements: 1D, 2D, 3D, and others. So I'll explain you about these three elements types in the upcoming slides. So let's start with others. Okay. So in the others, there are mass, spring, damper, gap, and rigid and constant elements. So mass element. So I'll just give you an example. Okay. So suppose you want to analyze a stool on which a particular weight is there. Okay. So the basically the design engineer asks you to see the stresses in the stool when you are putting a weight of 100 kg on the stool. Okay. So what generally you should do? You should model the stool. You should model the weight which is being put on the thing, and you need to give contacts between the stool and that weight, and then carry out the analysis, right? But it would be unnecessarily complicating the model, right? So instead of that, what you can do is you can find out the center of gravity of that mass which is being put on the tool, and then you can, from that center of gravity, you can couple the top surface of the tool, and you can apply that load, whatever is the weight of the tool. So in that case, that the amount of meshing which you might have required to mesh that component which is being put on the stool is removed right now, right? So in that case, the number of degree of freedom is reduced to one, or means a limited value, very small value. So in that sense, you are able to save a lot of element size, right? Similarly, comes to spring element. So spring element is also the same. Suppose for automobiles also, you might be seeing lots of springs in these cars and other automobile models. So you can also model it using spring elements. So if you're modeling a 3D spring, it will require a lot of nodes and elements. That also you can avoid if you're using spring element. Similarly goes with damper, rigid, and constraint elements. Now coming on to constraint elements, in softwares like Abacus, there is something called as a tie constraint. Okay, so suppose if you want to simulate a welded connection in the reality, so you can use tie constraint and you can do the same thing. So that's how it simplifies the things for you. Okay, now let's move on to 1D, 2D, 3D in the upcoming slides. Yeah, so how to decide the element type? So element type selection, geometry, size and shape, types of analysis, and time allotted for the project. So starting with geometry, size and shape. So for any analysis, the software needs all the three dimensions to be defined. Okay, so it basically, unless and until you are not having all the three dimensions to be defined, you can't carry out the calculation. Okay, so geometry can be categorized as 1D, 2D, or 3D based on the dimensions. Okay, so now starting with the 1D element, so it is used for geometries in which one of the dimensions is very large as compared to the other two. Just take an example of a long pipe or a shaft. Okay, the length might be very large as compared to the cross-sectional area, right? So in that case, you actually don't need to model it in a 3D way. So you can convert that, or you can assume that to be a 1D element. And instead of having a meshed it using a huge amount of nodes, you can restrict that to a two noded element, right? A long pipe of 1 meter of a particular cross-sectional area, you can restrict that to only two nodes. So in that sense, you are able to save the nodes by a huge amount, resulting in faster analysis, right? Yeah. So as an examples are long shaft, rods, beams, columns, and spot weld. Okay, see all these things are having one dimensions very large as compared to the cross-sectional area. So that's why you can assume this as 1D element. Okay, in 2D element, it is used when two of the dimensions are very large as compared to the third dimension. Okay, so 2D meshing is carried out on the mid surface. So in that case, yeah, so in that case, so you already have the two dimensions. So the only dimension which is missing right now is the thickness, right? So after while meshing, you need to only assign the thickness value, and you have all the three dimensions, right? So yeah. Now, why is 2D meshing carried out on the mid surface? To be very honest, due to the advanced capabilities which is being there in the softwares right now, you can. It is not necessary for you to extract in mid surface, but if you are carrying out analysis on a very big model, for consistency purpose, it's suggested that you extract from the mid surface. Okay, so till now mathematically what the software was doing was, if you are assigning a surface and you are assigning a thickness to it, it used to assign half the thickness to the top, remaining half to the bottom. Okay, so that is why it was mostly extracted at the mid surface. Okay, so as a thumb rule, when to extract a shell element is like when the thickness is consistent throughout and width to thickness ratio is greater than 20. Okay, now what are the limitations of shell meshing or 2D meshing? It is not recommended for path which is having non-uniform thickness profiles. Okay, yeah, this is an example of a 2D shell meshing. Okay, this car model is carried out using 2D shell meshing. Had you used a 3D meshing, it might have increased the element size by a huge amount. The number of nodes might have gone to a very high amount, means even above 1 crore nodes. So which would have taken means more than a week or 2 weeks or even months to solve a single analysis. Okay, by using shell meshing, you might have restricted the number of nodes to a lakh or 5 lakhs. Coming on to 3D element, 3D element can be used for all the cases. Okay, but generally you can use it when all the three dimensions are comparable. As an example is crankshaft engine components. These are very critical components. You need to check the through section stresses of the components or through section strains. So in that case, 3D element is suggested. Okay, now element selection based on the type of analysis. Now for structural and fatigue analysis, quad element, hex element are preferred over tria, tetra, and penta. Okay, for crash and nonlinear analysis, mesh flow lines and brick elements are preferred over tetrahedron. For mole flow, triangular element are preferred over quadrilateral. So what are this quad, hex, brick? I'll tell you in the upcoming slides. Okay, now for dynamic analysis, so whenever there is a, suppose there is a big geometry. Okay, suppose just take an example of a car. Okay, you can mesh it if there is an option that you can mesh it using 2D shell meshing or 3D. So always prefer 2D shell meshing. Why? Because apart from reducing the number of node count by a huge amount, it is also resulting in less stiffer elements, due to which it would be able to capture the mode shapes more accurately. Means dynamic analysis means what the prerequisite would be mostly model analysis, in which you would be capturing the mode shapes of that particular structures. So in case of shell meshing, since the stiffness would be lesser, so you would be able to capture the mode shape behavior more accurately. Okay, so that is the advantage. Now, time allotted for the project. So see, you need to understand one thing very clearly, that okay, quality of meshing and all those things are very important part of the thing of any analysis, but time allotted for the project is the main criteria if you want to be a successful CAE engineer. Okay, so that needs to be kept in mind for you, for each and every one of you. So when you are starting your career in this domain, or if you want to grow up in this domain, always make a habit of understanding the model first, understanding the requirement first, establish a timeline, and try to complete your analysis within the timeline. Okay, now suppose the product engineer says that okay, for an analysis which might have been actually taking some 100 hours, they are asking you to complete within 40 hours due to some urgent requirement. In that case, if you can't do a very structured high quality mesh, right? So you might have to make some compromises in the mesh. So in that case, these are some of the things which you can follow. So okay, instead of structured meshing, you can use the automatic and batch meshing tools in Hypermesh. Okay, for if you're carrying out 3D meshing, so see, brick elements or hexagonal elements are very difficult to mesh if the geometry is complex. So in that case, you can prefer higher order tetra elements in case of preliminary assessments. Okay, if assembly of several components is involved and only there are some components which are critical, so what you can do is you can mesh those components more properly. Other components you can mesh a bit coarser. Okay, yeah, or you can simplify the model using 1D, 2D elements, or the other types of elements which I told you, that is spring elements, beam elements, mass elements. Okay, so with all these things, you can simplify the model as much as possible and try to complete the analysis within the given timeline. Okay, now I told you about 1D, 2D, 3D elements. So, but can we solve the same problem using 1D, 2D, or 3D elements? Yes, we can solve. Means we can use 3D in all the cases, but the reverse is not possible. But yes, we can solve. But if we can solve all the analysis using 3D elements, why are we using 1D or 2D? So this is an example which will show you why. So just take an example of a cantilever beam of this dimension. Okay, subjected to a load at the end, and it is fixed at the other end. Okay, so see, since the length is very large as compared to the cross-sectional area, you can assume it to be a 1D beam. Okay, so in this, number of nodes are 2. You can also extract a shell actually because the thickness is very less. So you can extract a shell. So in that case, the number of nodes are 909, or you can measure it as 3D elements also. In that case, the number of nodes increased to 17,000. Just see the difference. It is from 2, it increased to 909 for 2D, then 17,000 for 3D. So this is a simple beam model I'm talking about. Just imagine when you are modeling components as big as an aerospace component or a car or any automobile component. Just imagine how many nodes, how much difference will it make if you are using a 3D element in the elements in which you can do with shell meshing also. See, let us see now. These are the results. Okay, So this is the analytical results, means results using hand calculations, which gives both stress and displacement. So in this case specifically, you are getting better results with 1D element, but most of the cases, but in most of the other problems, you would be getting get better results in case of 3D elements. Chances are very high. But for a 5% difference, is it worth to spend too lot of time? I don't think so. Okay. So because see, basically FEA is an approximation only. So it is very difficult to obtain the exact results. Okay. So time also is a very important factor which always needs to be keep in mind, okay, while carrying out the analysis. Yeah, so how to decide element length? So now I've told you what elements to use in which kind of analysis, what to use where. But suppose you started meshing, then what is the element size to be used? So there are three parameters for that. First of all, based on previous experience with similar type of analysis. Suppose being a CA engineer or you working in a team, you have already carried out a similar analysis. So based on that, you can use that value as a benchmark to start meshing with a specific mesh size. Okay, suppose if you don't know, you can discuss with your teammates or seniors and get to understand, okay, what is the mesh size being used for a similar problem. You can start with that. Or so depending upon the type of analysis. For linear analysis, you can mesh as fine as possible. But if it's a highly nonlinear analysis, which takes a lot of time, in that case, you need to keep a balance between the number of nodes and the time taken for analysis. Okay.
Yeah, hello.
Yeah.
Akhil?
Yeah. Hello.
Yeah, yeah. Sorry for interrupting. A little bit actually, the voice is breaking a little bit.
Who is it?
Yeah, you can speak now.
Yeah. Is my voice audible now?
Yeah, it's audible, but now a little bit it was breaking.
Okay. 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 So I'll just see. Okay.
Okay, you
Yeah.
can try now.
Yeah. 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 So let's continue then. So suppose if you're having no prior experience of carrying a similar type of
Yeah,
analysis,
just I think some small network issue.
is it still there?
Okay, please proceed.
Yeah. Okay. So in case of no prior experience of carrying out an analysis, so what you can do is first carry out a run with the default length. Okay. With the random number, you can just give a random mesh size based on your judgment. You can carry out the run. Okay. So then you would be getting some results, right? So there might be regions which are regions of your interest. Then what you can do is you can remesh them, remesh those stress regions, or and then compare the results by carrying out mesh sensitivity study. So what is mesh sensitivity study? You will reduce the mesh size in every iteration till there comes a point when the difference in the results are not that much. Okay, so that is called mesh sensitivity study. When the analysis is very complex and it's a very critical component, in that case it is always suggested to carry out mesh sensitivity study, and chances are that the clients might be even asking you to submit a mesh sensitivity report, okay, before they approve the results. So yeah, now how to start meshing. So before you start, don't just randomly or abruptly start the meshing operation. Okay, you first study the geometry, discuss with the design engineer or product engineer, understand the requirements, understand the problem, understand their expectations. After that, you estimate the time based on the requirements and based on your competency. You estimate the timeline. Okay. After that, only you start with the geometry check. Okay. So you start before starting with the geometry cleanup. You should first of all check the geometry. So for checking the geometry and models, it is also suggested that CA engineers should also have a basic knowledge of CAD. Okay. It will help you fasten up the process of geometry cleanup. Okay, so before starting the work, the geometry should be checked for free edges, scar lines, duplicate surfaces, small fillets, small holes, beads. So if all these things are there, you need to defeature them or remove them. Okay, you can do that on your own. But if there is an intersection of parts being obtained, okay, suppose there are two components, or suppose take an example of a gear tooth. Of there are two gear tooths, actually the gear tooth should be transferring the load from one tooth to another, right? But if there is actually an interference in there, then it would be very difficult to solve that analysis. Okay, so in that case, you don't need to do anything on your own. You intimate the same to the design engineers, understand, is it uh, was it actually intentional or was that a mistake? Then let them do it, and then you again start the analysis. Okay, so before you get any model, this, especially this interference, is a very important thing. So you need to always carry out interference check before you start with the analysis. Okay, then comes the symmetry check. Okay, so symmetry check means what? Okay, so suppose there is a complete model, and first of all, you need to see if you actually need to mesh the complete model or not. Okay, just take an example of this rectangle square shape with the hole. Okay, so even if you take the quarter shape, it is a quarter symmetric model, right? What does that means? Suppose you mirror this quarter shape, you will get a half this thing. If you mirror it once again, you will get the full model. So that means it has quarter symmetry, right? So what you can do is you can extract only this from that. You can mesh this, apply symmetry boundary condition to these locations, and you can solve the analysis, right? So in that case, you were able to reduce the number of nodes by 1/4. That's a big amount if the model is very big, right? Similarly, in this case, so see, this is a sector model. So you can take only one sector, in this case, 22.5-degree sector. So in that case, what is the advantage? You were able to reduce the number of nodes by a huge amount, right? So it is able to reduce your meshing time and effort. Okay, so with all the element selection methodologies I've told you till now, so I'll just give you an example. Okay, just take an example of this plastic bucket with a handle. Okay, so how can you mesh it more effectively? So assuming this to be a plastic part and the thickness is constant throughout, you can extract the shell and carry out shell meshing. Okay, now in the case of this handle, see, it's more like a beam with a very large length and a very small cross sectional area. So you can extract 1D beam in this case, and joining these two, you can join it using connector elements. Okay, so yeah, this is how simple it is. Okay, now these are some tips and tricks for meshing in critical areas. So see, location where high stress occurs, dense and structured mesh are recommended in that regions. Okay, so yeah, just take an example. Suppose this is a hole you want to mesh. So suppose you are the hole is in circular in shape, and if you're meshing it only using 4 elements, it is representing more like a square. So are you able to capture the actual geometry properly? No. So that is why you need to mesh it more fine. Okay, so generally minimum 12 element around the hole is suggested, but basically the organization I work, I follow minimum 16 elements around the hole to capture the mesh shape more properly. Okay, now coming, suppose you are modeling a fillet. In that case, around the fillet, you should be modeling minimum 3 to 4 elements along the fillet so that you are able to capture the curvature properly. Okay, now these 4 images are something called as mesh transition. Okay, so mesh transition means what? Reducing the number of elements from a higher value to a lower value. As an example, just take this. Here the number of elements were 3. Then using this mesh transition, you are able to reduce the element to 1. Okay, so these transitions always should be happening at a non-critical region. Means areas like fillets or these holes or some very critical region which are areas of interest, mesh transition should not take place. Okay, that you should ensure as an analyst. Okay, now in the 1D meshing, these are the different types of 1D elements: rods, bars, beams, pipes, and axisymmetric shell. So rods are basically tension. Rods can take tension and compression, so they can be used for truss members. In that case, you can use rod elements or shafts. For bar would be having all the 6 degrees of freedom, but it is only applicable to symmetric cross sections. So it can be used for shaft subjected to multi-axial loading, bolted and welded joints. Now coming on to the beam, the same like bar element only that it also supports unsymmetric cross sections. Okay, so that is shear center or warp pitch. Okay, now coming on to the pipe element. So basically, pipe element is something which is most commonly used in other CAE softwares like AutoPipe. Then yeah, AutoPipe is Caesar. Okay, these are the softwares in which these pipe elements are extensively used. So you might have heard of a profile of piping engineer. Okay, so piping engineers would be using this pipe elements extensively for their analysis. Then comes the axisymmetric shell element. So all these comes under 1D element types. Okay, So you can choose any of these based on your requirements and carry out the meshing. Now coming on to the 2D meshing, element shapes are generally either quadrilateral or triangular. Okay, so triangular means three-sided, quadrilateral means four-sided. So they are also further divided into linear order tria, higher order tria, or quadratic order tria. Similarly, quad, linear order quad, and higher order quad. Okay, so here the degree of polynomial is 2 in both these cases. Here the degree of polynomial is 1. So we don't go for a degree of uh, polynomial higher than 2 in the analysis we are carrying out. Okay, so this is what it is. Then the element types are thin shell, membrane, plane stress, plane strain, and axisymmetric solid elements. So okay, apart from you attending this seminar, so if you are attending for any interviews also, you please search about these three element types. I am pretty sure most of the interviewers would be asking this question to know your FEA knowledge. So plane stress, plane strain, and axisymmetric solid, you can just go through that also. Might be very helpful for you. Okay, now 2D mesh, how not to mesh. So these are some tips and tricks. Yeah, back-to-back triangles should be avoided. This kind of thing should be avoided. It should be a structured mesh. Mesh transition along the critical region should be ignored or should be avoided. Okay, these sharp elements at the corners or at the bolt hole should be avoided. Okay, so this is an example of a structured mesh. Okay, yeah. Now see, around the holes, you should be meshing it more fine to capture the hole properly. Suppose around the hole there is a washer also. So what you can do is you can carry out a split depending upon the size of the washer, and you can mesh it more finer. So apart from capturing the hole properly, you can also capture the washer surface properly. So yeah, these are some tips and tricks when you are meshing a whole thing. Okay. See, now coming on to 2D elements. So 2D elements are quad or tri means what? They are lying on one plane, which means what? Suppose you're taking a quadrilateral element, all the four nodes would be lying on the same plane, right? So, but if there is actually, suppose one of the node is lying on a higher end, means they are not lying on the same plane, that means it is not a proper quad element. So all that should also be ensured that there are no deviations or kinks. Okay. Yeah. So yeah, feature lines should be always followed, which means what? Okay, suppose you are meshing a sphere. Okay, so if you are meshing a sphere and you are meshing it and you are not able to capture the curvature of the sphere properly, that means you are not able to, the nodes are not lying on the edges. So that should always be ensured. Okay, so here are some examples. See, this is a zigzag line of a mesh. So this should be avoided. This is recommended. This diamond shape elements are not allowed. Okay. Yeah. Now for crash analysis, that is explicit analysis, which I talked in the beginning. So out of these two, this element might seem to be good for you, but actually this is not recommended. Why? Because see, the minimum time step required for solving the analysis in explicit is determined by the minimum length of the smallest element in this. So in this, the smallest element would be this. So the minimum length would be depending upon this. So which means that the time step would be very small. So which means it would be taking more time to solve the analysis. But here, since the length is constant, so you can, the time step can be a bit more relaxed to solve the same analysis. Okay. So that is why for crash analysis or explicit analysis, constant mesh sizes are recommended than having high quality, such kind of mesh. Okay. Yeah. Now coming on to the quality checks for 2D meshing. So as you all know that the results of any analysis is directly proportional to the element quality. Okay. Now ideal shape for a quadrilateral element is square. Square means what? All the sides equal, all the included angles, all the angles to be 90 degree. For triangular elements, it's equilateral triangle. All the sides equal, all the angles to be 60 degree. Right. So, but see, while meshing, exact meshing with exact square element or exact triangular element is not possible. So that is why there are some quality parameters like skew, aspect ratio, included angles, Jacobians. These are measures of how far your element which you have meshed is from the ideal shape. Okay. So there are some limitations which they have put. There are some factors which they have given. So if it is crossing those factors, that means you need to mesh it again or you need to remesh it. Okay. Now See, as I told you, it is not possible to mesh with exact square shape or exact triangular shape. That is why, means what the solver does it, they are converting all the individual elements of that model into the ideal shapes. Okay, then assigning a local coordinate system to this, solving the equation, and then again transferring back to the actual shape. So that that mapping from that factor which helps in mapping from the real shape to the ideal shape is called as Jacobian factor. Okay, so or distortion. Okay, so that is the thing. So I'll now tell you about the limitations or the factors, which is the limiting factor which is being used to check the quality. Okay, so first starts with warp angle. So it is the out of plane angle. Ideal value is 0, acceptable is less than 10 degree. Okay, so to give you an example, to tell you what is warp angle, so just take this quadrilateral. You draw a diagonal. So you draw two normals from these two places. Okay, so basically the normals, if they're lying on the same plane, the normal should be parallel to each other, right? But if they are not lying on the same plane, the normal would be forming some angle. So in that case, they have said that 10 degree is the maximum angle it can form. Else, the element quality is not good. Aspect ratio. It is a ratio of maximum length to minimum length. The ideal value is 1, acceptable is less than 5. Okay. Skew. So skew is what? Just give an example. You just take this quad. You draw two lines from the midpoints of these. The angles which is formed, 90 degree minus this angle, should be ideally 0. Means for a square, if you're taking a square, if you draw two lines, anyhow the angle would be 90 degree. So 90 minus 90 is 0. So that is the ideal shape. But since that is not possible, means so they have given a limitation of 45 degree. So that skew angle should not be greater than 45 degree. Okay. Yeah. So Jacobian, which I told you, that factor which is used in transformation, ideal value is 1. That means you have meshed within ideal perfect square, which is not possible. That's why they have given a limit of 0.6. Okay. So that thing should not be less than 0.6. Okay. Yeah. So skew included angles. So skew is based on overall shape and coming on to the individual angles. For example, for a square, the individual angle is 90 degree. For an equilateral triangle, individual angle is 60 degree, right? But since that is not possible, so they have mentioned a limit, acceptable limit. For quad, it's 45 to 135 degree. For tria, it's 20 to 120 degree. This is the range in which your included angle should lie. Okay. Now checks for 2D meshing. So suppose you have meshed the element. Now you want to check before submitting to client. You want to check if the mesh quality is correct or not, or good or not. So you can, for that, you can first of all check for free element edges, duplicate elements, duplicate nodes, shell normals, geometry deviation, and see while meshing in Hypermesh, while carrying out splitting operations, you might be creating some temporary nodes or free nodes. So that you need to delete. Then after you see, you might be carrying out meshing operation randomly from some places. Okay, you might be meshing one part of the component, then you might be meshing other part of the component. So in that case, when you mesh the full component, the node numbering would be haphazard. So which would be resulting in a very large matrix size. So if you renumber the source, if you need renumber the nodes properly, so it will renumber from one end to other end. So what it will result in lesser matrix size, which will result in faster solving. Okay. Then after that, after you mesh the whole component, you observe the family and types of nodes. Okay. How many nodes have you taken to mesh the full component, and what like how many percentage of elements are quad or uh, tria. Okay. So basically, for a good analysis, not more than 5% of the elements should be tria elements. Okay. If you are, if the requirements are very stringent. Okay. Yeah. Or the number of nodes should also not be very high. If the number of nodes are high, you need to take measures to reduce the number of nodes. Okay. Then check the mass. So see, you are actually carrying out FE analysis to capture the physical phenomenon into a virtual reality. Okay. So what is there in the actual condition should be matching. So the mass of the component in the reality should be matching with the FE model mass. Okay. So that is there. Then to check if the mesh connections are proper or not, you can Run a free run means model analysis without any boundary condition, or a dummy static analysis. Okay. So if there is any mesh connectivity issue, it will show up in that analysis result. Okay. Now let's come on to 3D meshing. So 3D meshing, different shapes are tetra, penta, pyramid, and hexa. Element types are solid. Degrees of freedoms are 3. So practical applications, basically 3D meshing can be used everywhere and anywhere. Okay. So yeah, so these are the 3D elements. This is tetra. It's a 4-noded element for linear tetra. Higher order tetra, 10-noded element. These are penta, higher order penta. Hexa or brick. This is a linear order brick. This is the most commonly preferred elements in the industry. Okay. Means if you're carrying out some higher order meshing, means high quality meshing. This is the higher order hex. These are pyramid elements. So basically, this is most suggested for all the analysis, or at least you can go with that higher order TET if you're carrying out a structural analysis. Okay. Yeah, these are some tips and tricks as how not to mesh. See, this is actually a curvature. So you meshed it using two elements, so it's not looking like a curvature, right? Basically, it means that you are not able to capture the curvature properly. So you need to mesh it more fine so that you are able to capture the curvature shape properly. As an example, this. Okay. So you meshed here using higher number of elements. So you are able to capture the curvature properly, right? Then suppose you are meshing a section or a plate. So through the section, minimum number of elements should be 2, basically 2, but we follow 3. Minimum 3 elements should be covered along the fillet or along the thickness, so that you are able to capture the bending behavior properly. Okay. Yeah. Now these are some of the quality checks for 3D meshing. So TET collapse. So this is the thing. So TET collapse means what? So suppose this is a proper TET element. So as this top node is coming closer to the bottom face, so basically it is no longer a TET element. It seems more like a planar element. So that means TET is collapsing. So that is what is meant by TET collapse. Volumetric skew. Ideal shape is 0. Acceptable is less than 0.7. What does that mean? Suppose you are taking this TET element only from the center, you draw a sphere. Okay, so all the 3 points should be lying on the sphere curvature. If that's not the case, so there is some skewness. So ideal shape should be 1. That means all the points should be lying on the curvature, but acceptable is less than 0.7. Okay. Yeah, Jacobian, same concept, but here the ideal value is 1. Acceptable is relaxed as compared to 2D meshing. It should be less than 0.5. Okay. Yeah. Now some of the key points. It is recommended to use quadratic tetra instead of linear tet in structural analysis. So as I told you, if there is a case in which you are not able to mesh with hexahedral element, you can use tetra, but ensure that you are using higher order tetra. Okay. But in thermal analysis, you can prefer linear elements also. Okay. Because why? Because in thermal analysis, there is only one variable, that is temperature. Okay. Now for hexa elements, ideal shape is cube. Okay. Now these are some of the quality checks. So warp angle, which is the same which I explained in the 2D element. So here the ideal value is also 0, but acceptable is a bit relaxed, which is less than 30 degree. Aspect ratio, ideal value is 1, acceptable is less than 5. Skew, ideal value is 0, acceptable less than 45 degree. So other checks, that is Jacobian and distortion, are same as the tetra meshing. That is ideal value is 1, acceptable is less than 0.5. Okay. So these are the things. Okay. So this is a basic preview of the meshing using Hypermesh, and a basic preview of the meshing concept in general. Okay, so yeah, thank you very much.